Hello, everyone, and thank you for taking the time to come to this early morning session. So briefly about myself, my name is Tim Durius. I'm a rendering engineer at Epic Games, and normally I work on things such as single-layer water, the water plugin, sparse volume textures, and other kind of niche features in a way. And last year, I got the opportunity to work on something really, really interesting, and that is the reason we're all here today, namely first-person rendering. Or to be more precise, native first-person rendering. This is actually a feature that we already shipped in Fortnite Ballistic last year, also in UEFN as the first-person device, and actually, excuse me, as an experimental feature in Unreal Engine 5.5. And actually, with 5.6, it has now gone into beta. All right, so let's look at the agenda for today. So first off, we're going to talk about what even is first-person rendering. Then we're going to explore the solution space to all the challenges that it poses. Then I'm going to describe how we solved it in Unreal Engine. And then I'm going to give you some pointers to how to use it in practice and how to make the most of it in your project, how to make the most of it for your project. And then finally, we have a short conclusion. And I'm going to try to leave some time for Q&A. Might be a bit tight, but I will hang around, so you can feel free to ask me questions afterwards. All right, so let's get right into it. What is first-person rendering about? So I suspect that most of you probably played a first-person game before, most likely a first-person shooter. This is what I'm going to be using as an example throughout this talk. But the things I'm going to talk about here, they apply to generally all first-person titles or first-person genres, maybe. So this is just the example that I'm using because that is what I had at hand. It's also the most common one, probably. So the idea is that we have a first-person perspective. And that means the player sees the world through the eyes of their player character, which means that they can see their own arms, the weapon that they're holding, and when they're looking down, legs and parts of the lower torso. And all of this comes with certain expectations and challenges. So let's dive into that. So the biggest and probably like the first challenge that you will run into is scene clipping. So first-person geometry should never clip with the scene. This is an expectation that players have come to have over the last few decades, I suppose. And I put an example of this on these pictures. So the top one is what you don't want to have, and the bottom one is what players would expect. They do want to peek around corners really tightly, and also they kind of have to get really close to walls. We need to give them that leeway because in a way players are kind of clumsy. So what I mean by that is in real life, when you're navigating your environment, you have a pretty good sense of where your limbs are in relation to each other and in space. And we're pretty nimble in a certain way when we navigate our environment. But a player in a video game, they need to go by what they see on screen. And also, if we're being honest, the controls that they have are kind of, well, rough. So in a way, players sort of move like a tank. So when they want to go through a doorway, we should give them, some leeway and maybe close one or two eyes to let them pass through that doorway, even though their huge sniper rifle would really block them from going anywhere. And on top of that, clipping would just look bad and it breaks immersion. But something to really keep in mind here is that what we're trying to achieve here is fundamentally non-physical. So the rest of our renderer is based on a world that makes sense to some degree. This does not. This makes no sense whatsoever. Okay, next challenge, field of view. For those of you who might not be familiar with that term, the field of view essentially describes the angle of the viewing cone of the player or the camera in the video game. And the thing about first-person titles is that players, especially on PC, often want to have a very high field of view in first-person games so they can see as much as possible of their surroundings, which theoretically gives them an advantage. The issue, though, is while this might look fine for the rest of the scene, it usually does look pretty horrible for first-person geometry. So again, I've put an example here. The top image is what it looks like when the scene and the first-person geometry is using the same field of view. And I like to call this effect spaghettified. So essentially, the arms are like way stretched out and the weapon looks kind of weird. And I'm fairly sure, I would hope so at least, you haven't seen this in an actual shipped game. So what you're usually more familiar with is the perspective that you see below. So actually, first-person geometry usually only looks good at a few specific field of views or like a narrow range of the field of view band. So next time you play another first-person title that has a slider to change the field of view, play around with it and pay attention to it. It will most likely only change the field of view of the scene, but if you take before and after screenshots and compare them, your first-person geometry, so your hands and your gun, will look the exact same. So they figured it out. This is also non-physical, but well, my gut feeling tells me it's not quite as horrible as the first one, but you know, it doesn't really make any sense. And it also poses questions like, if we're rendering the first-person geometry with a different field of view, essentially their pixels end up on a different location on screen, if you compare these two images. And now if the player tries to reach out to grab something in the world, how can you make that connect? It's like, that is a challenge. Many games need to get creative when solving this one. Okay, so let's pause for a moment here and look at how this is broadly very typically solved. So traditionally, the first-person player is just two floating arms in a gun. That's what games have been doing for, well, probably 20 years at this point. And it fixes the problem to some degree in a very neat way, because the first-person geometry is disconnected from the world. So you can never really touch anything except for the gun that you have in your hands, and that one is also considered first-person. You do not have legs, so you don't connect to the world in that way. So that means we can just render the gun and arms at a different field of view. And there are some downsides, of course, to this. Well, obviously, you don't have legs, and it usually struggles with shadows and reflections. So, you know, walking up to a mirror or receiving proper shadows, casting shadows, that sort of thing. It's not the same as the rest of the scene. But since it's disconnected from the rest of the scene, you cannot really tell in most cases that it's getting different lighting. Okay, challenge number 3, where are my legs? So I've just talked about this. Many games have shipped with just two floating arms and a gun. That looks fine, and to be honest, in most cases, players are not looking down. But it's the current year, and I think, well, in my opinion at least, high-quality first-person experience should have legs when you look down. But this is tricky because legs do connect the player to the world, so we need to figure out how to solve lighting and field of view and anti-clipping such that it still works with the legs, so that needs special handling. Okay, next challenge, lighting and shadows. So first-person geometry should receive the same lighting as the rest of the scene. So this one might seem like a bit of an obvious thing, but depending on how we want to solve the other challenges, this itself becomes obviously really challenging. Well, maybe not obviously, but well, it does say challenge number 4. Okay, it should also cast and receive shadows. And again, we cannot have two floating arms and the gun cast shadow on the scene. Otherwise, you know, the jig is up, players can see what's going on, and we can't have that. And lastly, reflections. So the first-person geometry should properly reflect the scene, but it should ideally also be reflected in the scene. So if you walk up to a reflective surface or a mirror, then the player should be able to see their full third-person self in that mirror. Many games do not have this for good reasons, but it would be nice if we could support this. And again, they should not see two floating arms and the gun in the reflection, as that, you know, would totally break things. Okay, so let's summarize our first-person wish list. So first off, we want a solution for clipping and field of view, so we can have these basic problems solved. Next up, the player should be able to see their legs. Lighting and shadows should all be consistent. The first-person character should cast shadows onto the scene and receive shadows from the scene. And finally, we want reflections to work properly. Okay, so at this point, you might be wondering, wait, what? How come Unreal doesn't have this already? After all, Unreal has its roots in, well, Unreal, which is a first-person title. So what's going on here? So actually, Unreal Engine 3 had a feature for rendering geometry in a different layer. Unfortunately, this was removed in Unreal Engine 4 due to complexity, and well, it's just plain difficult to make that work with deferred shading. And to be quite honest, this didn't really solve all of these challenges anyways. So the system that I'm going to present today is a big step up from what Unreal used to have. And actually, this also means that all the first-person titles shipped on Unreal since we removed this had to implement a custom solution or except like the scene clipping and no custom field of view. So, people had to get creative, and it's been long overdue that we fix this. Okay, let's explore the solution space. Okay, so I just said there's like a huge number of first-person games out there, and almost all of them really need to solve these issues somehow. So, just let's just take a look around and see what you can find on the market, so to speak. Okay, so first let's take a look at how we can represent the first-person geometry. So this is what I would call maybe headless. I don't know, like I came up with all of these names. There's like no official naming for this. But the idea is fairly simple. So we just chop off the player's head and place a camera there. It's straightforward. It has quite some advantages and disadvantages. So one of the advantages is we can solve lighting and shadows fairly trivially. We can just render the full body into shadow maps, including the head, and everything just works because it's essentially the same geometry in the same position in space. You get visible legs when you look down. I mean, it's all there after all. And you don't need to author separate animations if you already have third-person animations. But it doesn't really solve clipping or do anything for custom field of view. So I guess all of this is a bit besides the point. And also animations might be a bit too janky in first person. So usually what looks good in third person probably does not look good in first person. And it's actually kind of interesting in real life. We move around a lot, but I suppose our brain like compensates that and we don't really notice. But in a video game, people would probably get nauseous. That said, there are titles that have shipped with this, I think mostly in the simulation genre. So it is also a valid solution, and I guess it does depend on the content and you can tweak things. Okay, so next up, floating arms. You'll see this is like a recurring theme here. So, it's just two floating arms in the gun. No legs, so geometry is not connected to the scene, and that just means we can render it at a different field of view and use different lighting if we have to fix the other issues. And there's no visible mismatches since it's not connected to the scene in the first place. Then again, there's usually no shadows. Ignore that little shadow down there, it shouldn't be there. And it likely does need special first-person animations, but in my opinion, that is well-invested time. Okay, so let's look at the first solution that you would probably find if you start Googling for this. So I would call this one compositing, and it's fairly straightforward. So the idea is we first render first-person geometry into its own texture, and then we just composite that with the scene. So essentially, separate render target, and then just paste that on top. Sounds simple, but there are some challenges. Like, how do we compute lighting so it matches the rest of the scene? And like, how's that even supposed to work? Like, does it live in a separate world? And if it lives in the same world, like, how does that work? Also, it costs memory and performance. It adds quite a bit of additional complexity because now we essentially need to duplicate our rendering pipeline and run everything twice. And also, depending on how you set things up, if you just copy over the color, then the first-person pixels do not have a representation in the depth buffer. So, post effects or anything relying on depth cannot see the first-person geometry. But I suppose there are ways to fix this. Okay, next one. Like I said, I just came up with the names myself. I call this one separate render pass. So it's slightly more involved, but not terribly complicated. So the idea is we first render the first-person geometry, and then we set up the lighting pipeline such that scene pixels cannot ever overwrite a first-person pixel. So since we first rendered the first-person geometry, we guarantee that nothing ever will overwrite those pixels. And the way we can do that is what I would call depth stencil trickery. So one of the most straightforward ways of doing that is you just set a stencil bit when you draw the first-person geometry, and then when you render the rest of the scene into that same texture, you just check for that stencil bit, and if it's set, you just skip. What that gives you is a depth buffer where first-person pixels can essentially cut holes into the scene geometry or into the depth buffer. So imagine you're like face up against the wall and your rifle is sticking into the wall, further away from the camera than the wall itself. Then since we had this whole stencil thing, the wall pixels are kind of closer than the pixels of the gun. So what that means in practice is that things get really complicated when you come to transparency and VFX, because those, we cannot use stencil with them. If we could, like, they need to blend against the scene, and if they didn't need to blend against the scene, then they could be opaque. So effectively, what this means is when you stick your gun into the wall and fire, and you would normally have a muzzle flash effect, that muzzle flash effect will be depth tested away. Also, one issue that we have in Unreal is stencil is kind of tricky in Unreal, so many of the bits are already spoken for, and the meaning changes throughout the duration of the frame. And also, it's kind of hard to integrate with Manite. Like, it's not impossible, but it's hard to do it in a way that is still performant. So, might be good for other engines, though. Yeah. All right. So the next one is, well, kind of a generic thing. So the idea is we just use a custom projection matrix. The way that works is we just have a separate perspective projection matrix with the field of view that we want to have for first-person geometry. And then we can do some depth buffer trickery, which I'm going to go into next, to solve the clipping issue. So that solves both field of view and clipping. It doesn't do anything particular for shadows or legs connecting to the world, but it could be a start. It does, however, add additional complexity for maintaining a separate set of matrices. It's not terrible, but it does add some complexity. And you might be wondering, okay, it's just a projection matrix, but in practice, there's a whole bunch of stuff that's connected to that, dependent on it. So there's the view projection matrix, there's the inverse projection matrix, inverse view projection matrix. So it's like a whole bunch of matrices that are all dependent on what our projection matrix looks like. And I try to show this on the right. So the top one is essentially what the normal setup would be like, very, very simplified, for drawing the scene. And then essentially we sort of need to duplicate that and just do everything again and keep stuff around for the first-person stuff. Okay, so depth partitioning. This is the depth buffer trickery that I mentioned before. So this is very closely related to the custom projection matrix. And the idea is that we can reserve a range of the depth buffer for first-person geometry and remap the depth values. So I tried to show this on the right here. So that cube is supposed to be first-person geometry. In general, in the following slide, the cube is always first-person geometry. I tried to make something more fancy, but I'm a programmer, not an artist. So. And the green stuff and the house, that's supposed to be the scene. So on the top one is what it would normally look like, and the bottom one, we sort of squish the first-person geometry close to the camera. We sort of pancake it. And we make sure that the rest of the scene is outside of this range. So we sort of separated them. And this does solve clipping. The first-person geometry will always render in front of the rest of the scene, but how do we compute lighting on that? Our depth buffer values are all squished. So what we can do is we can undo the remapping, but then the whole renderer needs to be aware of this. Again, it's not like a fundamental problem, but it does add some complexity. All right, next one. This one is a solution for just the clipping. I call it scaling. Yeah, I don't know, naming things is very hard. So the idea here is that we scale the first-person geometry towards the camera. I tried to show this in the graphic on the right. By scaling it towards the camera, so relative to the camera itself in the view space essentially, we are also moving it closer to the camera. So, and that blue box around the camera, that is supposed to be the player bounding box. So really, if we can successfully move or scale the first-person geometry into that bounding box, we can effectively prevent clipping with the rest of the scene. Physics takes care of it for us. And you might be wondering, how does that even work? Like, wouldn't it look super weird? And yes, it does, but there's one exception. Exactly from the point of view of the camera, it looks the exact same because we're essentially scaling exactly towards the camera. The first-person geometry will still render to the exact same pixels, but if you were to look at it from any other perspective, it would be like super tiny and super close up to the camera. So internally, we called it the baby hands approach. Yeah. So now the question is like, how do we light this? So we kind of figured out that you can actually do the lighting on the scaled down geometry. Because usually light sources are fairly relatively far away from the first-person geometry, and also the size of first-person geometry is usually not that big, so you don't really notice the size difference that we're doing here. There's an issue with shadows. So first off, we can't use this to cast shadows, as we've had that bug. It looks very weird. Essentially, you see like a very tiny, tiny shadow on the ground, and people are wondering, okay, what's going on? It's like 5 pixels big or whatever. It looks like a mini version of the player. And shadows are also more binary on first-person geometry, so I'll get into what that means later. But in my opinion, it's not a huge deal. Okay, so next one, field of view, morphing or stretching. I don't know, it's like really hard to name these things. So the idea is that we can morph the geometry such that it looks like it was rendered with a different field of view. Okay, so the rest of the pipeline doesn't need to know about this, again, assuming that we're fine with lighting on deformed geometry. And this can solve visible legs with interpolation. So essentially, we stretch the geometry, but we can decide how much we want to stretch it on a per vertex basis. So we can interpolate along the length of the legs, whether we want it to be in world space or first-person space, so to speak. Again, this cannot be used to cast shadows, as that would also look kind of weird. Maybe not quite as bad as the other one, but still not good. And the way I try to visualize this is, so first look at the two cameras on the top. So the large field of view, essentially you have a larger cone, and that kind of rectangle cube thing is supposed to be our first-person geometry. And if you imagine it from the point of view of the camera, it is not filling up the whole screen. But if you narrow down the field of view so it gets smaller, it fills up the whole screen. And we can achieve the same effect while keeping the original large field of view, but just stretching the geometry so it takes up the same field of view. I hope that, again, I'm a programmer. All right, so our solution. First, let's talk about lighting full scale versus scaled down geometry. That was pretty much the first thing that we decided on what to do about that. So, like I said, some techniques calculate lighting with the first-person geometry at full scale. This gives correct and consistent lighting in most cases. In Unreal Engine 5, this actually results in normally clipping geometry looking weirdly dark. And actually this is because our lighting is fairly precise, not to toot our own horn too much, but if you think about it, it is kind of dark inside objects, if that makes any sense at all. Like assuming they're hollow, which I guess they kind of are in video games, it's dark inside. So I have a video here of this. Okay. You can see as I move into the geometry, it gets dark. Also, I implemented this with the stencil trickery I talked about earlier. So if you pay attention to the scope, it disappears because that is being depth culled. Okay, so lighting scaled down geometry. Like I said, the other techniques, they calculate lighting on the scaled down geometry. Lighting appears mostly correct in all cases. So that's a big difference to the previous one, where it always appears correct, but maybe not what we expect. The only catch here is walking in or out of shadow, the shadow appears and disappears very quickly on the gun, like the shadow that is received on the first-person geometry. Because really our first-person geometry is now very small, so in proportion, essentially, the shadow is much bigger. And so we move at a very high speed relative to the size of the gun. So kind of looks like it's popping on or off. So you don't really get that transition of the shadow across the length of the barrel. Maybe if you work very slowly, but in practice, this has not been much of an issue. It was never called out, really. Hold on. That video does not play. Here we go. So you can kind of see, if you pay attention, that it sort of pops on and off. Like I said, I've never got any complaint about this. But it is an artifact, potentially. Okay, so let's recap. Lighting full-scale geometry, correct lighting and shadows, normally clipping geometry will be back, and lighting scaled-down geometry, slightly incorrect lighting and shadows, but normally clipping geometry will look as expected. And this, as expected, is kind of very important. So, like I said in the beginning, what we're trying to achieve here is very non-physical anyways. So if we wanted to do it the correct way, the best thing we could have done is not do anything at all. But we're trying to do something that looks good to the player, and what players expect to see is not always what would make sense. So we're going with the right one. Okay, so our technique is based on scaling and morphing. We use it to solve clipping and field of view, and the way it works is we apply a matrix transformation after a world position offset is applied to the vertex, and before we apply the view and projection matrix. This matrix is constructed based on the scene field of view, the first-person field of view, and the desired first-person scaling factor to solve clipping. And the next slide, I'm going to give you a warning. I debated very heavily whether I should include it or not. Please don't be scared. Right, that's the morphing, essentially. Like, I'm interpolating between the morphed and non-morphed version. So first you get the spaghettified version, and then we slowly lerp that back and get what's looking better. Okay, now the scary part, or not so scary part, math. So I figured if you've come to this talk, you probably want to know all the details of how this works. Promise you it's going to be short and painful. Well, not really. It is going to be short, and it should not be painful, really. It's not that complicated. But feel free to sit this one out if you're not interested. It's just this one slide. I promise it'll be over fast. Okay, so if we look at things, scaling towards the camera is just a regular scaling operation in view space. So that's, uniform scaling. It's very, very simple. And if we look at how perspective matrices achieve field of view, they do that by applying scaling to the x and y components of the vertex in view space. So again, scaling. And if we combine these, really, scaling and morphing can both be expressed as a non-uniform scaling operation in view space. For convenience, we want this to be a transformation in world space, so we can apply it directly after world position offset and don't need to slot anything in between the view and projection matrix, which is usually handled kind of in other places in the renderer. So all of this actually results in a very simple 3x3 matrix. Okay, let's get into the juicy stuff. Okay, so first we just start with the FOV correction. And what we're trying to achieve here is this. So this is the, I would call, standard notation, more or less, of how we project a vertex from model space onto the screen. So the M is the model matrix that transforms from model space, the space in which the object was authored in like Blender or something, into world space. Then the V is the view matrix that transforms into view space, which is a space that is relative to the camera. And then the P is the perspective projection matrix. That one achieves the field of view and essentially makes things that are further away smaller. You will notice that I added this underscore FP. So that is supposed to be our first person projection matrix, the one with the field of view that we want to achieve. Okay, but what we're really looking for is this matrix T, which we can slot in between the model matrix and the view matrix. And the way we can construct that one is like this. So first we, again, transform to the view space and then apply our first person perspective matrix. So that first part is exactly the same that we have in the first line. And then we're doing something really interesting. We're going back from perspective projection space into view space, but this time using the inverse scene projection matrix. What that gets us is a position in view space that is essentially the delta between the two field of view projections. And then we again go back into world space because that is what we wanted. And now the rest of the regular pipeline, which is again view space and then normal perspective projection space. This looks all really long and kind of complicated, but if you squint your eyes, or maybe don't, you can see that these terms kind of cancel out with each other. So really what we end up with is this part. So the multiplication by the view matrix in the beginning and the inverse view matrix by the end, that is just for convenience. What we're really looking at here is that purple part, and that is what's correcting for our field of view. And now if you want to add scaling, like I said, it's just regular uniform scaling in view space. So we just really simply construct a scale matrix, where S is the value that the user selected, how much smaller they want to make the first person geometry. Slot that in there while it's still in view space, and we're done, pretty much. At this point, we can simplify things, and if you look at things, if you like sit down and take the time, which I won't do here, you will notice that this purple part also reduces to what is essentially a 3x3 scale matrix with this weird F parameter. So this is where it gets interesting. It's defined like this, and you don't need to think about it too hard, but if you look at it, like there is a term that depends on the field of view, that is a scene field of view, and a second term which depends on the first person field of view. And these are pretty much taken out of what the perspective projection matrix does to achieve field of view, and what both of these terms do together is we are essentially dividing out the scene field of view and multiplying by the first person field of view, very loosely speaking. But essentially that is the most important formula that makes this whole thing happen. So the final transform just looks like this: transform to view space, simple scale matrix, and then back to world space. Okay, scary math slide is over. Completely different topic. What about my legs? So there's multiple approaches. First one is a full first-person body where everything is connected. So your legs, torso, and arms are all, one mesh. That is actually what we did in Fortnite Ballistic. Not necessarily because it's the best or the only approach out there, but we have a lot of skins in Fortnite, and we couldn't really create a special version just for first person for all of these skins. That was unfeasible. So that is what we went with. But you could also create a separate world space lower body or a separate first person space lower body with a small caveat. All of them are valid approaches. So really do what fits best for your game and for your pipeline, I suppose. Okay, so let's get into the advanced features of our solution. So this one I call world space interpolation. Sometimes it is necessary to blend between world space and first person space. I put the space in quotation marks here, as it's not really a space. It's still world space, but we move things around a little bit. You can think of it like applying world position offset, but don't think on it too hard. The way you control it is with a custom material output, and that gives you control on a per vertex frequency. And this is particularly useful to interpolate the legs between world space and first person space. So what we want to do is have the feet, when you see that video on the right, which I'm about to play, the feet connect to the shadow that we cast onto the ground. And that shadow is cast by a world space representation of the player. So really, they should connect. And I'm going to interpolate between connecting and not connecting, and you can see what happens. Essentially, when the foot looks like it's up and floating, that is rendered fully with the first-person field of view. And since the first-person field of view is more narrow, it essentially moves things into another place on screen space. But we wanted to connect to the world. So the feet, when they are close to the ground, or like the part of the feet that connects to the ground, so generally the feet, I suppose, should always be in world space. Okay, next feature, we've just been talking about it, casting scene shadows. So the way that works is we've introduced the concept of an optional world space representation. So what that means is you can add, let's say, you can think of it as like a third-person version of the player. You add that, and you set these primitives to be world space representation. What that means is they are invisible to the player camera, and they are picked up by shadows. So it just works out of the box like that. And the way we do the shadows, just as like a side bit, is the shadows are rendered into a separate shadow map that is composited with the scene shadows that are cast onto the scene itself. So it sounds a bit complicated, but essentially there's kind of a big problem that we're running into here with shadows. And that is, we're casting shadows using a third-person version of the player. Now, maybe you might think, okay, where's the problem? If we receive that third-person version shadow on the first-person geometry, essentially what we're doing is self-intersection, kind of, because the first-person version of the geometry is slightly overlapping with the third-person in world space, but also different, otherwise we wouldn't need two versions. So what that means is, like, the arm can cast shadow onto itself. Like, both versions of the mesh logically represent the same object, but they're in different spaces in the world. So really what we want to do is make sure that the third-person version, like that world space representation, can never, affect the lighting of the first-person mesh. Okay, hardware ray tracing reflections. So we now have this convenient world space representation, and while we were at it, we just put those primitives into the ray tracing world, into the BVH, and what that gives us is that Lumen reflections can now see the third-person version of the player. So that works straight out of the box. You just walk up to a mirror, and Lumen can see the third-person you. This also works for ray traced shadows. They pick up shadows cast by these primitives. And since it's in the ray tracing world, it can really be used by any ray tracing feature. Currently, these are the two that have explicit support for it, but it could be trivially added to other features in the future, like mega lights, for example. All right. And like I pointed out for the shadows, the same goes for the reflections. Rays originating from first-person pixels, so reflection rays essentially, must skip the third-person geometry. Otherwise, for example, a reflection ray starts from your arm and then hits the third-person version of that same arm, and you get like weird black reflections on it, and it just looks all kinds of weird. Keep that in mind. Okay, first-person self-shadow. You might be wondering, wait, what, more shadow? Yes. So, so far we have shadow casting on the ground. We can receive shadow from the scene on our first-person geometry, but what we're still missing is the first-person geometry casting shadow onto itself. So that is, for example, in this image, the scope casting shadow onto the weapon and onto the arm. Many games actually do not have this. And our solution supports all light types, and currently it is implemented with HZB screen tracing, but in theory you could also use dedicated shadow maps. So since it's implemented with screen tracing, the usual screen space limitations apply. But in practice, it looks pretty good. I suspect it's because all the relevant shadow casters are on screen anyways. So didn't really have any complaints so far. So here's some before-after images so you can get the effect that this adds. So this is with lighting only, and this is the full shading. So many games actually have something like this. You can, next time you play some other title, play around and, put the light source to the right of your screen. And then if there's still, like a specular reflection on the inside of your left hand, then okay, they're not, doing this. And personally, I think it adds a lot, especially on the movement. But we'll get to that in a moment. Okay. But this one is a bit of a downer, to be quite honest. For these advanced nice features I just talked about, we need a bit in the G-buffer. So in particular, casting shadows onto the scene, and also the hardware ray tracing reflections and the first-person self-shadows. They all need a bit, so we can tell whether a pixel is first-person or a scene pixel. But there's no more free bits in the G-buffer. Unreal is very complex, has a lot of features, so all the bits are already spoken for. This was quite a challenge. So I'm not super happy with the result, but we essentially came to a compromise. Without static lighting, there are some free bits related to baked shadows, so I just went ahead and stole one of those. But I realized that there's still obviously a demand for baked lighting, especially for the shooter genre. Unfortunately, this was like a really tight constraint for us. Like this was a very hard challenge to solve. And I suggest that if you have the engineering capacity, you can change this. So it's just a few lines in some shader files. And I would suggest you maybe kick out capsule shadows if you don't need those. They have a special bit in the G-buffer. Or if there's some other feature of the renderer that you do not need for your project, but you absolutely do need static lighting, then you can swap out those bits. Shouldn't be too invasive of a change. Hopefully this changes in the future. I'm not super happy with it, but it is what we had to do to ship things. So yeah, in practice, if you want player shadows on the scene and hardware ray tracing reflections, you need to go to the project settings and disable allow static lighting. It is unfortunate, but it is what it is for now. Hopefully it changes in the future. Yes. Okay, so here's a video with all of it put together. So you can see face up against the wall, no clipping. lighting and shadows all look consistent. You can see your leg looking down, shadow properly connects to it. And also if you pay attention to the self-shadow, I really like that effect on the movement, like how it moves. Okay, so let's talk practice. So first, let's start with the basic setup. So you simply tag first-person primitives as such. The way you do that is we've introduced a new first-person primitive type property that's on all primitive components. It's that lower image that I put here. And it has 3 values. None, which means it doesn't interact with the first-person rendering feature at all. This is what you want to use for the majority of your objects, essentially anything in the scene. Then there's first person, so that is the player body that they see in first person and the rifle or whatever they're holding in their hand. And then finally there's world space representation. I'm not super happy with that naming, but you know, it's a recurring theme. Naming things is very hard. It made the most sense to me at the time, really. And that one you should use for the mesh that you use to cast shadows and the one that's visible in reflections. Then next up, you want to configure the field of view and scale on the camera. So it's really that simple. There's like 2 new properties. I've also added like 2 checkboxes to enable it on demand if you need to toggle it on or off for some reason. And that's it. You're done. Like it's that simple. And another thing about setting things as a first-person primitive, I've said before that if you set things to be a world space representation primitive, it's invisible to the first-person player camera. It's still visible in the editor, but if you go into the first-person player camera, it will not be visible. And conversely, first-person primitives, they do not cast shadow onto the scene. Otherwise, it will look very weird, and I couldn't really foresee any case in which you would want this to cast shadows onto the scene. So the renderer automatically disables this. So if you set something to be first-person, shadows will disappear until you enable these other substitute shadow effects that we've just talked about. Also, they will not show up in the ray tracing world, like the weirdly deformed first-person meshes. So you don't need to worry about any weird shadows or reflections happening there. It should all be working out of the box. Set up that world space representation and should all work. Okay, dealing with legs. So you can use separate geometry for the lower body. I've put a picture of what that might look like on the right. And then you can keep it in world space, but don't forget to disable casting shadows. Otherwise, you might be in for, some torso-less legs walking around in the shadow world. Or you can have it be in first person and apply the world space interpolation to get the feet to connect to the ground. Alternatively, what we did is, use a single connected first person geometry for torso, arms, and legs. In any case, you should probably watch out for camera intersection with the torso, especially when looking down. So unfortunately, I don't really have any silver bullet advice for that, except that you probably need to tweak things and sort of make sure that either the camera can't move low enough or move it a bit forward as you tilt down. Yeah, unfortunately, this is yet to be solved in a consistent way. Okay, adding self-shadow. So the way that works currently is it's implicitly enabled if the light is set to cast shadow. There's a console variable that you can find in the documentation for scalability, so you can control which light types should cast first-person self-shadow. And the way this works in terms of performance is lights only incur cost if they actually affect the first-person geometry. So if they effectively overlap the player, you can think of it like that. So that means if you have many overlapping lights and then you walk through their sphere of influence with your player character, then the cost of all of these lights will accumulate. So that is probably what you want to look out for. But on the flip side, if you have a bunch of lights in the scene, local lights, and they do not overlap, you can only ever be affected by one light, and that's, pretty harmless. The way first-person self-shadow is enabled per light might change in the future. So this was a feature that came in very, very late in development. So yeah, it's not set in stone, essentially, how this is controlled. We did think about adding a checkbox per light, but then the feedback was there's already way too many checkboxes for shadows on lights. So yeah, TBD. Okay, setting up a world space representation. So essentially what we want is a fully animated third-person version of the player character. And if you have a multiplayer game or already have something like this for NPCs, then you're in luck. you don't need to really do a whole lot of stuff at this point. You only need to look out really that the animation of the legs should match between the third person and the first person version of the body. As again, we use the third person version to cast shadows onto the scene. So we really want the first person legs to connect exactly at the same point in time or along the timeline of the animation when the shadow version is also putting its foot down essentially. And the way you set up this world space representation is you just create the primitives, like the actor for it, and then you set all the primitives on that actor to world space representation. It's that simple. Okay, so about some practice pointers and tips. Camera parameters. So the first person scale should be as big as possible and as small as necessary. So small scales might require adjusting the camera near plane because we are scaling towards the camera and not the near plane. I'll get to that later. Making it smaller. And making it smaller makes the shadow transitions more binary, and at some point, if you push it too much, it can also lead to precision artifacts. So really try and figure out how small you need to make it and try and not to make it, as small as you can make it, essentially. And finding a good setup for first-person geometry is tricky. So maybe different weapons might look better with different field of views, or they might require different scaling. So I would recommend setting up your game in such a way that you can have a different field of view and a different scale per weapon. And then when you switch weapons, it just snaps between them. Okay, so first-person rendering is a feature that is also fully integrated within the material graph. That means, for instance, that the transform position node can now also transform to first-person space. This is useful if you want to, for example, calculate where the reticle of a scope would be in a post-effect material. So the way we do the scope essentially on the weapons in Fortnite is it's like a post-processing material and that draws the scope texture. And if you have the rifle in like hip mode, not ADS, then you kind of need to figure out, okay, where should that reticle be on the screen? And for that, we need that node. Okay, next up, queries. So there's a new isFirstPerson node, which pretty much does what it says it does. It tells you whether the current primitive is first person, so you can do any custom logic that you would want to do. You can also query whether a given opaque pixel is first person with the scene texture node. This does require the gbuffer bit that I talked about before. So if you do have baked lighting enabled, or if you've changed things and do not have the gbuffer bit, which is also true on mobile, then it will just always return false or 0, I guess. And lastly, you can use the view property node to grab the first person field of view and scale that's set on the camera if you need that for any case, for any reason. All right, next up, interpolation. So that first person output node, like custom material output node, is not strictly required to do this. Alternatively, you can also use the material attributes workflow and set the interpolation alpha value through that. So we had to add this because custom material outputs can only be used in like a parent material and not in a material function. And so now you can also set this in a material function, and you do not need to change your parent material if you have like many different materials, as is the case for us in Fortnite with all the different skins. You just need to have a single material function that's used by all of them. You can slot this in there, and it takes care of it. So how do we drive this? You could use vertex painting to drive the world space interpolation, essentially just paint a gradient along the length of the legs. That is sensible, and I like that idea. Unfortunately, all the vertex channels in Fortnite were already spoken for, and also would probably mean that artists would need to go through each skin and repaint things. So we instead did something slightly horrible. We defined an analytic mask based on the height of the pre-skinned vertex position and its distance to the vertical center line of the bounding box. So that's quite a mouthful, but essentially what we did is we did some math to figure out, based on the pre-skinned vertex position, does it belong to the legs or not, assuming that legs are like roughly in the lower half of the bounding box and sort of in a cone, because in our skin position, the arms kind of go like this. So you need to be careful not to include, the hands. So it's kind of not so nice. So if possible, I would recommend going with the vertex painting approach. or if you're creative and find some other idea how to drive this, feel free to do that. Okay. Also, I would like to call attention to this single new blueprint function that we've added. It's called transform world to first person. And it essentially, you pass in a world space position and it tells you where it would end up on screen, or in first person space, and then if you project that on screen, if it's rendered with first person. And that is particularly useful if you want to spawn actual projectiles. So normally your gameplay code would maybe spawn the projectile at the tip of the gun, where it thinks the tip of the gun would be anyways. And you want it to be in world space. So, but you want it to look like as if it comes from the tip of the first person gun. So you can use this blueprint function, figure out where that is, and just spawn it at that position instead, and it just works. Also, something I've sort of neglected to point out before, this first-person rendering feature actually works for most primitive types, almost all. So it also works for particle systems and Niagara effects. So you can just set your muzzle flash effect to first person, and it will automatically show up at the right place, and also benefit from anti-clipping. So really, you can jam your face into the wall and pull the trigger, and the muzzle flash will still look as expected. Okay, in conclusion, we've implemented a full first-person rendering solution that solves custom field of view and scene clipping. It's fully integrated with lighting, shadows, and reflections. You get visible legs, and all but the advanced features such as shadows and reflections work on all platforms. So the anti-clipping and the custom field of view, you can use that on mobile. And we've already shipped this in Fortnite Ballistic and UEFN, so it is battle-proven to an extent. And now it's even in beta. As for future work, this might come as a bit of a shocker, but it's not too bad, I promise. Nanite is currently not supported. What that means is if you tag a mesh as first person and that mesh is Nanite, it will instead fall back to the, fallback geometry. So this is not an inherent limitation to the technique. It's just, honestly, we ran out of time. And the aim is to implement this by 5.7. Nanite just needs a bunch of special magic to make this happen. Again, it's not set in stone, it's no guarantee, but that is what we're aiming for, 5.7. And the other thing is fixed function post effects, such as depth of field, screen space ambient occlusion, that sort of thing. Currently do not do anything special for first-person pixels, and usually they do rely on depth buffer values. And since we've did horrible things to the first-person geometry, those do not really necessarily make any sense anymore. So far, no complaints, but it might require some looking into. And once we fix these two things, we want to go production ready. So the current aim is to do that in 5.7, but again, no promises. All right, at this point, I would like to take a moment and thank some people. First off, the Epic rendering team who supported me. Then the Fortnite first-person team, whose feedback helped shape this feature, and also whose work really enabled me to show all these nice images in the first place. So they did a really awesome job. And finally, everyone else who made this session possible. Thank you very much.